Let us understand the fundamentals of cyclic voltammetry. It consists of cycling the potential of an electrode that is immersed in an unstirred solution of the electroactive species and then measuring the resulting current. The potential of this working electrode is controlled versus a reference electrode such as a saturated calomel electrode or a silver-silver chloride electrode. The controlling potential which is applied across these two electrodes can be considered as excitation signal. The excitation signal for CV is a linear potential scan with a triangular waveform as given in figure. This triangular potential excitation signal sweeps the potential of the electrode between two values, sometimes called the switching potentials. The excitation signal in figure causes the potential first to scan negatively from plus 0.80 initial potential to minus 0.20 volt versus saturated calomel electrode, at which point the scan direction is reversed, resulting a positive scan back to the original potential of plus 0.80 volt. The scan rate as reflected by the slope is 50 mV per second as shown in figure. A second cycle is indicated by the dark line. Single or multiple cycles can be used. A cyclic voltammogram is obtained by measuring the current at the working electrode during the potential scan. The current can be considered the response signal to the potential excitation signal. The voltammogram is a display of current, vertical axis, versus potential, horizontal axis. Since the potential varies linearly with time, the horizontal axis can also be thought of as a time axis. This will be helpful in understanding the basic principle of the technique. A platinum working electrode is a solution containing 6.0 millimole of potassium ferricyanide as the electroactive species in 1.0 molar potassium nitrate in water as the supporting electrolyte. The potential excitation signal used to obtain this voltammogram is shown the figure, but with the negative switching potential of minus 0.15 volt. The initial potential of plus 0.80 volt applied at A is chosen to avoid any electrolysis. The potential is then scanned negatively, forward scan, when the potential is sufficiently negative to reduce ferricyanide. Cathodic current is indicated by B due to electrode process ferricyanide to ferrocyanide. The cathodic current increases rapidly, B to D, until the concentration of ferricyanide at the electrode surface is substantially diminished, resulting the current to peak, D. The current then decays D to G as the solution surrounding the electrode is depleted of ferricyanide due to electrolytic conversion to ferrocyanide. The scan direction is then switched to positive at minus 0.15 volt for the reverse scan. The potential is still sufficiently negative to reduce, so the cathodic current continues, even though the potential is now scanning in the positive direction. When the electrode becomes sufficiently strong oxidant, ferrocyanide which has been accumulating adjacent to the working electrode can now be oxidized by the electrode process, ferro to ferri. This causes anodic current, I, to K. The anodic current rapidly increases until the surface concentration of ferrocyanide is diminished, resulting the current to peak, J. The current then decays, J to K, as the solution around the electrode is depleted of ferrocyanide. The first cycle is completed when the potential reaches back to plus 0.80 volt. Now the cyclic voltammogram is obtained. It is clear that any potential positive of 0.40 volt would be suitable as the initial potential in the reduction of ferricyanide would not occur when the potential is applied. This procedure avoids inadvertent electrolysis as a result of applying the initial potential. In the forward scan, ferrocyanide is electrochemically generated from ferricyanide as indicated by the cathodic current, while in the reverse scan ferrocyanide is oxidized back to ferricyanide as indicated by the anodic current. A more detailed understanding can be obtained by considering the Nernst equation and the changes in concentration that occur in solution adjacent to the electrode during electrolysis. The potential excitation signal depends on the ratio of ferricyanide-ferrocyanide at the electrode surface as described by Nernst equation for a reversible system. The important parameters of a cyclic voltammogram are the magnitudes of the anodic peak current type and cathodic peak current type, PC, and anodic peak potentially, Pa, and cathodic peak potentially, PC. These parameters are labeled in figure. One method of measuring IP involves extrapolation of a baseline current as shown in the figure. The establishment of correct baseline is essential for the accurate measurement of peak currents. It is generally difficult for more complicated systems. The peak current for a reversible system is described by the Randall-Sevcik equation for the forward sweep of the first cycle, where I sub P is peak current in ampere, N is electron stoichiometry, A is area of the electrode, centimeters square, D is diffusion coefficient, centimeters score per second, company is the concentration, mole centimeter cube, and nu is scan rate, volt per second. I sub P is proportional to concentration if all other parameters are kept constant. The relationship to concentration is particularly important in analytical applications and in studies of electrode mechanism. The peak anodic current and peak cathodic current should be identical for a reversible system. The average of peak anodic potential and peak cathodic potential will give the standard reduction potential for the redox system. The diagnostic test to decide the reversibility of a redox reaction by cyclic voltammetry is provided in the table. Please check the A. Criteria for reversible system, B. Criteria for quasi-reversible system, and C. Criteria for totally irreversible system. For more details on the cyclic voltammetry, please refer to David Harvey, DePauw University, Analytical Chemistry 2.1 book or https://chem.libretexts.org/courses. Please give your valuable suggestion in the comments section to improve the learning and content. Keep learning and thank you.